Okay, so much about communicating classes. Now let's talk a little bit about another property uh, of our Markov diagrams, that is irreducibility. So Markov chain, or for that matter, a transition matrix P, is said to be irreducible if I communicates with J for all ij that form part of our state space S. That is, the chain is irreducible if the state space S, uh, forms a single communicating class. So here's a question for you. Do you know an example of an irreducible transition matrix P, maybe from the continuous world? Well, there you go, right? So this is typically um, the way we model nucleotide evolution, and as you can see here, this is irreducible in a single class because it can go from any state, any nucleotide state, to any other nucleotide state. Okay. Now another thing that is important, that's the equilibrium. Uh, we saw that if x0, x1, x2 is a Markov chain with a transition matrix P, then xt is distributed according to P transposed, so the transposed vector of the prior probabilities, and then it follows that xt plus 1 is distributed according to P transposed multiplied with the transition probability matrix P. So the question here is about the equilibrium. If there is any distribution P at some time t such that P transposed multiplied with the transition probability matrix P equals the transposed vector of the prior probability. So this is this equilibrium property where we say that, well, apparently the influence of the P matrix, of the transition probability matrix, doesn't really matter anymore. So we are in some sort of stable state with respect to the probability distribution of xt. So then, if this is the case, so if P transposed multiplied with the transition matrix P equals P transposed, then xt is distributed according to the prior probability vector. Xt plus 1 is also distributed to the prior probability vector. Xt plus 2 is also distributed according to the prior probability vector, etc., etc. So we're in some sort of stable state. And basically, so if we're at a point where P transposed, so the transposed vector of prior probabilities multiplied with the P matrix equals the transposed vector of prior probabilities, and if xt is distributed according to the prior probability vector, then all following probability distributions are identical. So, in other words, what this tells us is that once a Markov chain has reached this distribution, this prior probability distribution, it will actually stay there. So it will attain a stable state, right? So that's what we call the equilibrium state. Basically, nothing changes anymore in our Markov process. So the distribution does not change anymore. So this is what I just said. So if we have this equality that holds, we say that the distribution, prior probability distribution P, is an equilibrium distribution. And as I just said, equilibrium means, or balance for that matter, means that there will be no further change in the distribution of xt as we wander through the Markov chain. An important note here is that the equilibrium does not mean that the actual value from the state space, the actual value xt plus 1, will take equals the value of xt, right? So it just means that the distribution of xt plus 1, the probability distribution of the xt plus 1 is the same as the distribution of xt. So for example, to give you an example, so the probability of being in state 1 at time t plus 1 equals the probability of being in state 1 at time t, and this is the first entry of our prior probability vector. Then again, the probability of being in state 2 at time t plus 1 equals the probability of being in state 2 at time t, and this is identical to the prior probability, to the second entry of our prior probability vector. So this is something very important. Okay, so here is an example. We're given this Markov diagram here with its states and transition probabilities, and we're given the transition matrix here. And let's suppose that we start at time t equals 0 with all states being equally distributed. So we assume that we have the same prior probability of being in state 1, 2, 3, or 4. So this is basically just the same as a Jukes-Cantor model, where we assume that A, C, G, and T have the same prior probability. In any case, so the chain is equally likely to start in any of the 4 states. Now if we look at the first steps and consider the probability distribution for being in state 1, 2, 3, or 4, right? So at time step number 0, because we just assume this prior probability distribution, all are equally likely. And then we run our Markov process. Time 1, the probabilities shift for being in the 4 different states. At time 2, those probabilities shift. At time 3, etc., etc. And so now what we're actually interested in is to find the point in time where those changes between the probability distributions here between steps like t and t plus 1, so where those changes are not visible anymore, right, in plain words. So where this probability distribution remains constant from step t to step t plus 1. So if we run that long enough, if we just simulate it, you can write like a computer program. Here we're now considering the probability distribution of being in different states after 500 time steps, 501 time steps, 502 time steps, etc., etc. And now you can see that this probability distribution remains constant. And so this means that we've actually reached the equilibrium of our Markov chain. And so the interpretation of that is that the chain has actually totally forgotten about the initial probability distribution, the prior probability distribution, that all states are equally likely. So you run the Markov chain long enough and it will forget about the initial conditions. So there are several, and like a nice exercise if you like programming, would just be to write a little simulator for this Markov chain that just executes a lot of simulations and then gives you those probability distributions here. Okay, so there just as a side note, there are several other names for an equilibrium distribution. So if our transposed vector of prior probabilities is an equilibrium distribution, it's also called an invariant, so it doesn't really change, or it's also called a stationary distribution. So basically the chain stops here. It doesn't make any sense to run it for more time. Okay, now how do we go about calculating the equilibrium distribution? So one example here is that we can explicitly calculate the equilibrium distribution by solving this equation, right? Under the restriction that the sum over all entries in our prior probability vector is 1, and all prior probabilities must be larger or equal to 0. I will spare you the details of the calculations now, but the equilibrium frequencies now for our example diagram back here, the equilibrium frequencies of this are the following: 0.28, 0.3, 0.04, and 0.38. Okay. So what happens when we converge to equilibrium to our nice probability matrix? What is happening here is that each row of our transition matrix, p to the power of t, sorry, there's a typo here, so this should be, the t should be raised here. So each row of our transition matrix, taken to the power of t, converges to the equilibrium distribution we've just calculated as t, as the number of time steps, goes to infinity. So all rows actually in our transition probability matrix become identical. So here's a nice diagram, once again for the same example, showing you the impact of starting points, right? So here, this is just the number of time steps t, and here those are corresponding lines for being in the 4 different states, and this on the y-axis here is the probability, the conditional probability of being in state k, so in one of the 4 states, after time t, given that we started at x0. And so x0 here is explicitly set at 2, as 2 in the first graph, and here we always kind of, we start running our Markov chain from state 4. So what you can see here is that the initial behavior is actually different because we just start running our Markov process from different starting points, but then in the end it always kind of converges to the same equilibrium distribution. And so this is also something that you can observe for continuous time models. So this graph here shows you the convergence of our Jukes-Cantor model to its stationary distribution. So here now we don't have discrete time steps anymore, but continuous time steps. So this is our branch length, and this is the transition. This is the probability of observing a certain state given, so state j, given different starting states. So here here we would approach that from the top. So basically we run our Markov process for some time and we end up at this equilibrium frequency at a branch length of 2.0, 2.5, where our Markov process, even if this is continuous time, but our Markov process has completely forgotten about its initial state, right? So here the starting state and the state we're interested in the end, whose frequency we're interested in the end, are identical. Here we start in a different state, so let's say that we're interested in the state A, but we started in T, then it will also converge to the equilibrium frequency, either from above, if we started in state A and are interested in the frequency of state A here, and from below if we started in state T, let's say, and are interested in the equilibrium frequency of state A. So the probability of ending in state J when starting in state I over time, or branch length ni, is shown here where I equals J for the blue curve and I does not equal J for the red one. Okay, and then another question here is that, well, is there always convergence to an equilibrium distribution? Do we always converge to equilibrium or not? So let us consider this graph here. In this example, p to the power of t never converges to a matrix with both rows being identical as t becomes large. So because it just jumps around between 2 states, the chain never forgets its starting conditions as t goes to infinity, because p to the power of t has this form here if the number of time steps is even, and p to the power of t has this kind of inverted form, so to say, here if t is odd. So this will never, it's always flipping between those two transition matrices. So this will not converge. Okay. However, well, the chain does have an equilibrium distribution, p transposed of 0.5 and 0.5, but the bad thing is that the chain does not converge to this distribution as t goes to infinity. So it does have an equilibrium distribution, right, over time. It's very evident by looking at this. Half of the time will be in this left state here, and the other half of the time will be in the right state here. But the chain will never converge to this distribution as we go to infinity. Right. So what are the conditions for convergence? So if a Markov chain is irreducible and aperiodic, so here we have the concept of periodicity, and if an equilibrium distribution exists, then the chain will converge to this distribution as the number of time steps goes to infinity, always regardless of the initial starting states. So remember that irreducible means that the state space is a single communicating class, as shown here, whereas here, well, we have a kind of non-irreducible Markov diagram, right? So what we said here about convergence only applies to irreducible Markov chains. Okay, now we still need to define periodicity. So in general, the chain can return from state I back to state I again in t steps. So this basically means that for some t, for some number of time steps, the probability of starting in state I and ending in state I must be larger than 0. And so this leads to the following definition. The period di of a state I is given by di equals the greatest common divisor of t, given that, well, pt from I to I is larger than 0. So this is the greatest common divisor of the times at which return is possible, return to the original state I is possible. So the definition of periodicity is that we say that the state I is said to be periodic if di is larger than 1. So, and for a periodic state I, the probability of being in state I, ending up again in state I after t steps if we started in state I, is 0 if the number of time steps t is not a multiple of its period. So then a further definition here is that, well, we say that the state I is said to be aperiodic if di equals 1. And so, for instance, our nucleotide substitution models are aperiodic because we always have a probability, a non-zero probability of remaining in the current state. Okay, so here's an example. What is the period of state D, of state 0 here? What's the period of getting back to state 0? So this is the greatest common divisor of the sequence 2, 4, 6, etc., right? Because I could go from state 0 to 1 to 2 and then go back again. So this means 4 time steps, or I could go from state 0 to 1 and then back again. This is 2 states, or the other way around to -1, then back to 0. So basically I take the greatest common divisor of this sequence here, which I can see very clearly that it's just all even numbers starting at 2, and so the period of this is 2, and we say, and this chain is also irreducible, by the way. Okay. So the result here is that if a Markov chain is irreducible and it has one aperiodic state, then all states are actually aperiodic. So the theorem tells us that, well, let x0, x1, etc. Be an irreducible and aperiodic Markov chain with a transition matrix P, and suppose that there exists an equilibrium distribution P transposed. Then from any starting state I and for any end state J, the following holds. So if the starting state is I and the end state is J, the conditional probability of observing J after T time steps, given that we started in I, converges to the prior probability of observing the equilibrium distribution of P as T goes to infinity. So in particular, the transition probability matrix P raised to the power of T converges to the equilibrium distribution as T goes to infinity for all I and J. So P to the power of T converges to a matrix with all rows being identical and equal to the transposed equilibrium distribution. Okay, so why are we actually interested in this? So the stationary distribution gives us information about the stability of a random process. That's why we're interested in that. Okay, right, so now we're done with that part on discrete Markov chains. And now we're going to talk about continuous time Markov chains, how we make this transition from the discrete world to the continuous world. So the main difference here is that those transitions or this switching or those jumps between states occur now at random times and not like at discrete clock ticks as in a CPU, for example. So basically we do not have any periodic oscillation, but we do have this concept of waiting times until a transition takes place. So here, if we take into account those waiting times, what we want to do in order to be able to consider continuous Markov chains is that we want to understand what happens as with our waiting time we go toward an infinitesimally small time dt, right? Now the other difference here is that we write our transition probability matrix as a function of the continuous time t, right? So now this is written so that you know that from phylogenetics from our models. This is now the transition probability matrix given time or branch length t. Here this is time p0 and this is our time axis. Then basically what we want to consider is what happens at time dt, like if an infinitesimally small increase in the time, and then a time p of 2 dt, etc. So the transition probability matrix is a function that returns a matrix, right? So this is just like a transition probability matrix. However, what you should keep in mind is that most standard maths on scalar functions, although this is kind of a matrix function, but most standard maths on scalar functions can still be applied. Now let's look at the derivative of this transition probability matrix for time dt and compute the limit as delta t goes to 0, and then, well, we just apply the standard formula for computing a limit. So what you should keep in mind is that only dt is a scalar value in this, or delta t, so this is written with the Greek letter here, is actually a scalar value, and everything else, the p's here, are matrices. Okay. And so keep in mind, or note that the derivative of a matrix is obtained by individually differentiating all of its entries, and the same actually holds for calculating the limit. Right, so calculating this limit, delta t goes, for delta t going to 0, requires solving a differential equation. And so if we can solve this, then we can actually calculate the transition probabilities for time t. One thing you should remember here that holds for discrete chains is our Markov property, right? That going from state I to state j at time 2 is just the sum over all possible paths of overall intermediate states k here. And so this is also known as the Chapman-Kolmogorov relationship and can be written differently as p to the power of n plus m equals p to the power of n times p to the power of m for any discrete number of steps n and m. So how do we kind of take this into the continuous world now? Right. So this holds for any discrete number of steps n and m, and thus for continuous time, what we want to hold, the property we want to hold, is that, well, we want the transition probability for going from state I to j in time t plus h to be just the product of the two transition probability matrices. So the transition probability for going from I to some intermediate state k in time t, and then from k to j after some time h. Right, so let's go back to calculating the limit. So if we say that this property shall hold, right, so this is the Chapman-Kolmogorov relationship, we want this to hold, we can rewrite our equation for the limit here. So p, the transition probability of t plus delta t, as the transition probability given for t multiplied with the transition probability of delta t. And then if we move our transition probability matrix for t outside of the bracket here, what we end up with is the transition probability for time delta t minus I, which is just the identity matrix, so this is just analogous to 1 in the scalar case, right? So here are some examples of like a 2 times 2 and 3 times 3 identity matrix. And now what we actually see, right, because we're interested in the limit for delta t, the limit doesn't depend on the transition probability matrix P of t, so it just depends on this transition probability matrix for delta t here. And we'll see that this is actually very helpful here. So now if you actually look at this, this is the very famous Q matrix. So the instantaneous rate matrix we see in all of our phylogenetic models. And the values of Q can essentially be anything, but the rows must sum to 0. And this is just a consequence of the fact that the rows of P must sum to 1. So we're kind of subtracting 1 here in every row, so they must be 0, right? So this is kind of very straightforward. So now you know why the rows of this instantaneous rate matrix Q must actually sum to 0. So what we have so far is that if I differentiate by dt, so an infinitesimally small time, I get that I need to compute the product between pt and q. So q is also called the jump rate matrix, or as I said before, the instantaneous transition matrix, or instantaneous rate matrix. Now imagine for the time being that the transition probability matrix for time t is just a scalar function, and q is just some scalar constant. And in that case, I can compute P of t just as the exponential of q times t, right? And so actually exactly the same thing holds for matrices, only that computing this matrix exponential is a little bit more complicated than it is for scalars. So calculating a matrix exponential is not trivial, and it's not just taking the exponential of each of its elements, right? So that doesn't work. Basically, what you write is that you to start with, you just write down the series expansion of the exponential with this Q matrix and the identity matrix included here. So this is basically what you need to solve. So one simple way of doing that, so if you want to write like a phylogeny program quickly, would be to say, oh, okay, I will just kind of approximate this matrix exponential and take maybe whatever is shown here, and just forget about the rest, and this should give us a sufficient approximation of our transition probability matrix, which maybe is not such a bad idea, especially if the matrix exponentiation for some reason is very complicated. Right. So if we want to compute the matrix exponential like this, but the bad news is that there's no general solution to analytically calculate it. So it really depends on the properties and on the shape of Q. So in some cases, we can come up with some analytical equation, so just write it down, like for the Jukes-Cantor model, so there's an analytical solution for calculating that. For the general time reversible model of nucleotide substitution, we already need to use some creepy numerical methods, so eigenvector eigenvalue decomposition, which are known to be difficult, and we might actually discuss later how we do that for the GTR model. And well, for non-time reversible models, so now we're talking about nucleotide substitution models, the matrix exponentiation is even more difficult. Right. Now, going back to the equilibrium distribution, so assume there exists a row vector, P transposed, such that Pt multiplied with Q equals 0, then this row vector P, so the prior probabilities, is actually the equilibrium distribution of our model, and that's what we typically see with kind of our prior base frequencies that we use in our models. This is the equilibrium distribution. Okay, and so this, with a short introduction on continuous Markov chains, I'll end this lecture.